So welcome, and I'm glad you're here. I'm going to go ahead and switch over to my slides here. And I'm really excited that I still have the opportunity to share this with everyone. It's something that is near and dear to my heart, is getting excited about STEM, but also being curious about it, looking around the world that we live in and seeing where the STEM applies. Just a couple things. As Eric said, chat is a really big component of what I want to do today. I'm sad I don't get to talk to you in person, so I really hope that everyone sends messages to all the attendees. That way we can hear from each other and learn from each other. At certain points, I will be using wait time. So I'll tell you, type everything that you want into the chat, but please wait to hit enter, because just like I would want to give wait time to you if you were in person, I want to give everyone at every speed of typing the opportunity to get their thoughts out. So with that in mind, you should know that I teach high school pre-calc. I also teach an inquiry-based physics class this year, and oh my gosh, I can't wait to show you the cool things my students are doing, and an advanced geometry class. I geek out on STEM. I see it everywhere around me, and I can't help but talk about it. And one of my favorite questions that students ask is, when are we ever going to use this? So let's get started. This is the fun part. This is all of my students one day, a couple weeks ago. We went out and bought a bunch of toy race car tracks and said, here's the thing. You've been studying all this physics. It's time to be curious about it. So we handed them each a box, put them in groups of 3, and said, go make something, and then start exploring the physics behind it. So I want to take a moment to ask you, when you look at this picture full of all these race car tracks, what STEM curiosities do you have? And we're going to employ that idea of, please type it into the chat, but hold off on pressing enter for a good 45 seconds. I'll give you just a moment to think through what questions you have, write down as many as you can, and then hold off on the enter. That way we have time to process our own thoughts before we start reading everyone else's. So I'm going to stop talking for a good 30 seconds, and then I'll give you a heads up of when to hit enter. So I'm not gone. I'm just practicing some wait time, and I can't wait to see what you say. There's my timer. I didn't want to start too soon. So if everybody could hit enter, and we'll start to see some of these cool questions. I got a question sent to us, is, are the tracks for cars? And yes, they are for little race cars like Matchbox cars. And then we have a question that popped up. What's the speed of the cars going down the track? How does the track layout impact all of the speeds? See what other questions we have. Kathy says, there's lots of questions about trajectories. What are the energies of everything? The forces, friction. What could we do to investigate it? What inquiries could we have? We have a practical question. How expensive was it to get all the materials for this? How did we grade it? Did any of them say it was too kiddish? Ooh, how could we use video to measure this? These are all awesome. I will come back, Chris. This is a great question. So one of the questions was, how expensive was this? And at the very end, I want to talk about kind of my budget for all of these projects, because when I first started brainstorming this session for when we were going to meet in Dallas, we were going to use a lot of sensors. We were going to do all these cool things and explore things that we hadn't gotten to try before. And then when it became online, I started looking around my house and trying to figure out, what do I have in my own home that if we start online teaching, I can still get kids inspired, and maybe they have it in their own homes to run their own analysis. Or so these are all great questions, because I think that's part of why we're meeting like this today, is we're trying to find new inventive ways to tackle teaching STEM, and it might be in a situation that's different for us. So all of these questions are really great. And a lot of my kids had the same question about, what is the speed of the car going to be? Or what is the friction on the track? And so what we realized, I teach this with a co-teacher. I have a math background, he has a physics background, and together we're doing this cool new inquiry class that's different for both of us, and it's been so rewarding. So when we had the kids do this, we were thinking they're all going to ask about speed. But then they started to say, wait a second, when I'm up at the top of the board, I think there's a different kind of energy when I'm holding the car versus when it's running through everything. And so this is how we started our conservation of energy chapter. So what I want to do is I'm going to switch over to my TI-Nspire and share a little bit about what they did. When we had the kids run their little Matchbox cars from the very highest height that they had down to the very bottom, we realized that for us to truly understand what was going on, we would need to do a little bit of, we would need to collect some data about the actual velocities that we were seeing and compare it to what we would predict based on that height. And so to do these calculations, here are all of their actual velocities that they measured along the track. And the way that we set this up is that they would measure every 90 centimeters along the track. And depending on how they had built it, that could have meant different heights. So every student's group data was a little bit different. And that made it really interesting to look at the overall generalness of this experiment. They also had to find their car mass, which we had them put in kilograms so that we could get the correct velocity in meters per second. And then we assumed that the gravity was 9.8 meters per second squared, or the gravity acceleration. So these heights are all in meters over here. And actually, one thing that my students don't realize is if they have the student software, sometimes changing it out of document preview up here in the right corner and putting it in computer preview, it's just a little bit easier to see everything on the screen. So I'm going to do that because as a presenter, I always like it when everyone can see my screen. So we're going to answer one of the questions there about energies. And for any physics teachers who might be out there, I think you're like chomping at the bit. You're like, man, I know that this is a bunch of mechanical energy and we have some potential energy right there at the beginning, and then as it starts to move, it's building and it's kinetic energy. And we have formulas to think about what we would predict these would be. So we would find potential energy by taking the mass times the acceleration due to gravity and multiplying it by the height. Of course, I have this in a spreadsheet because I really want kids to learn the skill of a spreadsheet. I think it's a great skill that we can teach them before they head out to college, especially if they're going into a STEM field and they have to collect a lot of data and analyze it. This is a great way for them to get their feet wet. So we can take our car's mass, and because I want to keep that same mass the whole time, we're going to go ahead and put in our dollar signs, and that locks it into that cell right there, which is awesome. We're going to take that mass, and I always do dollar signs. I know you don't have to, but I tell the kids that this is my weakness. I can never remember whether the dollar sign goes in front of the first one or the second one, and it doesn't hurt to put them in front of both, and that way I don't have to remember. I'll remember the formula for potential energy due to gravity instead of worrying about the spreadsheet notation. So that's why I have the double dollar sign. Even though it's superfluous, it's in my mind easier to remember it that way. So we have our mass of the car, and we're going to multiply it by the gravity, the acceleration due to gravity. And again, we're locking that value in because we in Ohio do not have to worry so much about higher elevations. In Columbus, Ohio, it's pretty flat. I did just see that we had a question from Kathy, and I appreciate that. How did they measure the velocity along the track every 9 centimeters? That's a great question. And actually, I don't know if I misspoke, but it was 90 centimeters along the track. a lot of the kids, we try to just give them free rein over all of our sensors and encourage them to find their own best strategies. We originally were using the motion sensor, the CBRs, and we realized we were getting a lot of noise because the kids were running alongside of their cars and they couldn't help themselves. They wanted to see the entire trip down the track. So instead, we switched over to using the little BSPs. I don't know if you've ever heard of them, but it's spelled BEESPIS. And you can just actually set those right over the track. And they did a great job of recording the velocity as it came down the track. So Kathy, great question. So what we have up here is me not typing everything in quite yet. We have the potential energy due to gravity is equal to our mass times our acceleration due to gravity times the height. And when the kids realize that they can just click on that box and it fills in that value for them, they geek out. Now, of course, it's a common mistake to forget to put the enter inside of it or the equals inside of it. And then they're like, well, I'm just getting this formula again and again. And so we talk about the skill of putting the equals out in front. And then when they learn that that little cross in the bottom corner right there lets them drag it down and perform that same calculation 6 times very quickly, oh man, you have just given them the best present in the whole world, because they're like, I don't have to type it in my calculator again and again. No, because conceptually, we want you to get the big idea of it. So they're pretty excited about all that. Then we know that as long as a system is closed and we're not introducing any work into the system and we're not having it leach out with friction, then potential energy plus kinetic energy should give us our total mechanical energy. So we're going to make an assumption here. We're going to assume, because these are my physics students who are seeing this for the first time ever, we're going to let them assume there's no friction on this track. And that means that the total mechanical energy should equal what our potential energy due to gravity was to start. So we're going to say that this is always going to equal this amount. And because it's always going to equal that single value, we're going to put the dollar signs in front of that as well. So we have, let me go ahead and get this moved over just a little. There we go. So we're going to go ahead and find that cross and just drag that down. And the total mechanical energy for the system with that assumption of no friction is going to stay right here. Well, again, due to the conservation of energy, we know that our potential energy due to gravity plus kinetic energy should equal mechanical energy. And so we're going to take the mechanical energy and subtract our potential energy to get kinetic energy. Now, this is a great conceptual piece to this, because yes, I could have students do that once or twice or 3 times in their calculator, but if they really understand the formula for it, then they can apply it in spreadsheets. And here we go. So I'm going to pause for a minute. That was a nice little, like, me geeking out on what we had done. But I want to get your thoughts. How many of you use spreadsheets with your students, either in math class or science class or art class? For any class, does anyone use spreadsheets with their students? And I want to hear from the I want to go ahead and hear in the chat. Jackson, awesome. I love hearing that you use spreadsheets in your algebra classes, because, oh my gosh, like, if they can get that skill when they're in 9th grade, then it doesn't seem intimidating at all. And it really is about conceptual understanding. And Jessica's like, yes, of course we use these in biology. Oh, awesome. So using them for I got to scroll up for a second, using them with measurements of some, for example, resistance in batteries Kathy, we might have to chat. I'm going to learn about that a little more because we're going to do circuits. And Ohio is almost assuredly going to be doing online school while we're doing circuits. So this might be a great chance to connect. And Mr. Bird over here says, definitely. My students discovered that on the handheld, you can even use Control-Click to grab the crossing arrow down. That's so helpful. A little bit in computer science. This is awesome. So we have all sorts of STEM fields using spreadsheets and helping students see that it's not just a big table, that it's actually a working, fluid piece of mathematics is awesome. So the last piece of this is that we can go ahead and calculate the predicted kinetic energy, or sorry, the predicted velocity based on our kinetic energy. So I'm going to go ahead and put predicted velocity, because I'd like to be able to check these out. And that's going to equal the square root, which you'll have to, in general, I teach them the commands SQRT, not because they don't have it on their calculator, but if they want to translate the skill over to any other spreadsheet. And fundamentally, I want to get them ready for all things. And I think this is a great tool to do that. So I teach them about square root. So I'm going to take the square root of 2 times the kinetic energy. And I'm going to use the cells still because I know I've defined kinetic energy up front, but I don't really want to define it or multiply it by everything in that table because then I'll have all this empty space in the bottom. So for right now, I'm going to leave it this way. And this is going to be divided by our mass. And our mass was this cell right here. And that's always going to be locked in. And so as we would predict, there's going to be a velocity of 0 at the very beginning because we believe that it's all potential energy until we release it, and then it's going to get going faster and faster and faster. Except I have a calculation error because I want this to be square root over the whole thing. I looked at that 19, I'm like, they were moving, but not that fast. That's a good thing for students, too, to make sure that their answers look reasonable. Yeah, 3 meters per second sounds a lot more reasonable for a toy car, so we should be good. So the great thing about this, and I'm going to switch back over to handheld, is now we get the chance to actually see how this looks. So if we add a new page and go to data and statistics, what I'd love to see is for every one of those times, or every one of those heights, then let's go ahead and look at our velocities. So we have the predicted velocity, but I really want to see how predicted velocity stacks up against the actual velocity. So I'm going to add another y variable so I can take my actual velocity and definitely see something crazy happening at the end here. And so I love to throw this one back at my students. I say, you look at this and you say, that just can't be right. That just can't be right. Well, look at your own picture. And why wouldn't that be right? So I'm going to give you a little insight that maybe you didn't get to see before in the big picture because there was a lot going on. I'm going to stop sharing this for just a moment. I think you can clearly see that the actual velocity all of a sudden has a huge spike toward the end. And it said for the predicted velocity that it should be slowing down. That feels off too. I'll have to look at that. But one of the interesting things about this experiment is that we also had them put a loop-de-loop in it. So if you look at this right here, the kits that we bought, and they were, I think, $6 or $7 on Amazon, but the kits that we bought had this loop-de-loop in it, and it actually had a little elastic piece that as the car went into the loop-de-loop, it accelerated it out. So it increased the amount of work in the system. And so you're starting to see some changes in their data based on that, which was awesome. Because sometimes having a routine problem to start off the thing, sometimes that can be good, but it can also be really nice to throw a loop-de-loop in the middle of the problem and have students start pondering a little bit more. So these were all the things that the kids had to take with a little bit of guidance from us, and then they were working on those spreadsheets. So I'm going to pause for just a minute. In this experiment, I think a lot of things that we say are STEM are really one component of STEM. It's either a really great science lesson, and by the way, you don't have to do every component of STEM to have a great lesson. It's just that I would encourage us to try to find ways to develop all of these together, because this holistic understanding of how things work together, I just see that as best preparing students. So once again, I'm going to take another about 30 seconds of just quiet wait time. And I want you to think about, granted you didn't get to see the whole activity, but based on what you heard described and based on that picture you saw, what were the different components of STEM in this activity? Could you name something for science and for technology, for engineering and for math? And maybe which ones were blended? So I'm going to stop talking. I'm going to put my 30-second timer on once again. And if you could go ahead and just pause on pressing enter, we'll give everyone time to think through everything, and then we will we'll all share out. I'll tell you what, timers on myself have been one of the best things ever. I always tell the students at the beginning of the year, the timers are never for you. They're just my way of making sure that I stay quiet for long enough to give you time to think. So now, since we've had a little time to think, looking through here, we've got some physics, energy conservation, absolutely, some science with gravity, and the technology and math, and everything is kind of incorporated into that spreadsheet. For technology, we've got the building, the measuring, because don't forget, you can go low tech with this as well. A measuring tool is a type of technology, even though it's low tech. We actually had to build the track. Exactly right. They had to find, some of them were going with extreme curves, and they realized that their car was flying off every single time. And so going back in and making those revisions to make sure that the car could complete the track was really, really important. Definitely, the math involved some algebraic formulas in this and understanding how everything was happening. Gosh, I love this. Also, I feel really, really great about this chat. Like, I miss connecting with everybody, but just seeing what everybody brings to the table, like, this is awesome. And Jessica says, you know, you're using data analysis in math as well, which is a growing field that we've been talking about a lot in math. What does this look like? How do you keep it really engaging? And so absolutely. So, and Mr. Bird adds, Sean adds that there's a retesting component to this. And I think that that's really important, because in science, we need to be able to run our experiment again and again and again and again and revise it. But sometimes in the math class, I think we're so product-based that we don't, and this is a generality, so of course it doesn't talk about everybody, but sometimes there's a stereotype that in math we're trying to get to a product, and so we don't always go through the revision. And I think that's a beautiful component of STEM that strengthens everything else, and so I really love that you included that. It's also a really nice intro to my next slide, so I gotta say, shout out to Sean for helping set me up. That was not arranged, I promise. But in every one of these problem-solving frameworks, and I've done a little bit of research on this because I was wondering, what is the overlap in how we think about problem-solving in science and when we're using technology and we're collecting data and creating models? So I pulled 3 of my favorites. The good old scientific method, which, I mean, this is like the first problem-solving framework that we really are accustomed to learning, and it kind of stays with us, I think. And then in the past couple of years, we've been working on more and more frameworks for understanding this push for mathematical modeling and this push for incorporating more statistics. So I'm going to give you just a moment to read over these. And then, as I've done it in the last couple times that we've run the chat, I'm going to stay quiet. But this time I'm going to stay quiet for about a minute because I want you to observe whatever stands out to you in these problem-solving frameworks, and I want that to be what you share in the chat. So this is a bigger question now. What are you getting from these problem-solving frameworks? What do you find interesting? And I'm going to pause myself for a minute to give you time to think. Definitely have to get in and check that timer. My kids play with my timers all the time, and I never know what I'm going to hear. So what I'm hearing from all of you is that I gotta get to, oh man, there were so many good things said. I just got to go ahead and get to the top of the chat there. So let's see. There's a lot of similarities between the three. Rebecca says, you know, all of them talk about this need to ask questions and that you have to start with your own questions, analyze it, and then interpret what you've seen. And I think that, Rebecca, you're spot on. Every single one of these says the interactor with the science or with the math should be the one posing the questions. And I hope that you're recognizing that that's a big goal of this presentation as well, because it's not enough for me just to, I love bragging about my kids. I would do it all day. Like, these students impress me continuously, but unless you have the chance to look at what they're doing and ask your own questions, I think it's less meaningful. So Rebecca, thank you so much. Absolutely. And you know, Sean, I think that a lot of us in STEM get passionate about the analyze portion. You know, we're like, oh my gosh, I want to make sense of things. Like, math is so clear and you can get it. And so I think that's where we geek out on. And so that's why I really love that these start with the idea of asking a question. And Sean, I admit that we probably don't do the same for math, that we don't always iterate our way through the science. And you'll even notice in the scientific method that it says test your hypothesis, but it doesn't always say the word iterate. We would hope that you would run multiple trials of a certain experiment, but it's hard to sometimes push ourselves in our classrooms to take the time to do that. And I tell the students that's why I have multiple groups running the experiment. So you should be sharing it as if those are multiple trials. We have some different phrasing in this. And you know what, Kathy, you're right. The scientific method, it specifically says you have to communicate your results. And I think that that's something that they've been revising the GAZE framework and trying to add that component into it a little bit more too in the past years, because it's not enough to interpret it. You really have to communicate about those so that everybody can get what you're trying to do. And Jessica says flat out, you got to be curious. You know, for every single one of these, you have to be curious and then do something and try to figure out, like, what does it mean? And all of these, Hassan is saying, you know, this isn't about just getting kids to think in one way. We're trying to have them think across the disciplines, like how do we make connections? And the analysis part of it really, a lot of times in our physics class, the analysis relies on something they just learned the day before in pre-calc. I have that as a blessing because I teach some of my kids in pre-calc and physics, and I can try to tie those experiences together. And I think what all of these are pushing for is a deeper understanding, that this idea of just glossing over it to check off that we had done it, that's not good enough. Like, for real problem solving, we need to go deeper. So that was awesome. I really appreciate everybody's insights to this. I geek out on these because I think that when I get into my groove with teaching, sometimes I don't think as much about having students pose questions. And when we look back at this, it's a good reminder of our pedagogy of how are we going to do this best. So moving on. Another thing that we do is we decided to play pool. And we got on Amazon and we found like this 4-foot pool table, and my co-teacher and I were like, okay, we can't buy one for every kid. Like, how are we going to manage this? How are we going to set this up? And so we got this little 4-foot pool table, put it on the teacher's desk, like cleared everything off and said, okay, students, we want to figure out what's happening when you're playing pool. And of course, side note, the geometry teacher in me is geeking out because you've got those angles of incident and reflection, and I'm like, oh, this is awesome. But I kept my focus. I stayed true to the physics of it. And we told our kids that we wanted to use this app called Motion Shot. It's a free app. Any kid can download it. And our setup for this was, we're going to take the first pool shot, but we want you to figure out how you can film this. How can you make sense of it? What do you think you're going to see? And I'm going to pose that to you as well. So if all you have is an app on a cell phone and a 4-foot pool table, what STEM curiosities do you have? I'm going to pause. I'm going to do the 30-second thing. Go wild with this, everybody. Think about your geometry self. Think about your physics self. And then in about 30 seconds, we'll check out everybody's comments. And time flies when you're having fun. So I was reading all of the chat, which is also helpful for me to be quiet so I can just enjoy it. So one of Kathy's questions is the velocity going to be constant? What happens with impulse? Is there energy conservation happening here as well? Does this have something to do with conservation of momentum? What's the frame rate going on in here? Jackson says, I'm hoping you showed the billiards from Donald Duck in Math Magic Land. Oh, darn, we didn't. Everybody asks me, have you shown the Donald Duck stuff? And I'll be honest, I don't know that I've actually seen it. So maybe that's my homework for spring break, is to watch that movie. Oh yeah, definitely a little bit about trajectories and thinking about this as, you know, could I put a great big grid on this thing? Awesome. And what Hassan says, you know what, I would check out the distance between the stick and the ball. Would that affect it when it's hitting it? And a left-hand shot is a good example of why you might put spin on a cue ball, hit it low, and it'll back up and not go to the side pocket. So all of these things are really interesting. And I'll be honest with you, to get these couple pictures, there's this art, right, to inquiry-based learning, because you know that you want kids to have great questions. You want them to experience it, but also you have a goal in mind. And every once in a while that requires setting it up in a certain way. And so my physics teacher, he was like, I'll tell you what. See, Sean's over here posting homework for me. I'll have to get on there later. I'll copy that link. So my physics co-teacher said, I'm going to go ahead and shoot it because I don't want spin on it. I don't want for this to be one of those situations where kids are just trying to get them all in the pockets. So he's actually the one shooting this. but the kids had to tell us about how they thought we should video this. And one of the nice things about the motion shot is you actually see it in live time start to fill in these different frames. And Sean asked what was the frame rate for this, and I think it's 260 frames per second. No, that was slow-mo on the iPhone. I'll look it up. It's a great question. But how many frames per second are you getting here? And the kid said, you know what, let's just stand on a desk and hold it right over, and we'll put it up on the AirPlay. We'll AirPlay it to the screen, and everybody can watch it in live time. It'll be just like you're at a sporting event and you're watching live pool, and it's really fun to see them tackle this idea of how can you have this tiny little pool table and not everyone can see. Well, they just came up with this way to get everyone involved, even though it was a physics teacher shooting pool. So we took these images, and I ended up doing something I never thought I'd do. I geek out all the time as a geometry teacher about the geometry app on the Nspire, but I also didn't think I was going to use it as much as I do here in physics. So one of the things we were trying to do is we were trying to specifically talk about the conservation of momentum. And so we found the mass of 2 of the pool balls and found that the masses were exactly the same, which was helpful because if you're talking about momentum, then it's mass times velocity. So now we can look at these velocity vectors. Since we know that they have the exact same frame rate because they have the same number of pictures, and on motion shot you can control how many frames out you go, we actually found the velocity vectors for the y component in the positive and the negative direction. And you'll notice they're pretty close to each other, which is what we would expect with the law of conservation of momentum. So I thought this would be kind of a nice thing to share with my colleagues of how I did this. And so we're going to go ahead and add in a doc. And I'm going to make it a geometry page. I'm also going to pull up the chat on the side here because I love seeing what everybody has to say. And then this is one of my favorite buttons ever. This insert button here, I use it more than I ever thought I would for that feature right there, image. So we put in the image, and this one, I think, nope, that's the earlier one. I want to try this one out. By the way, I geeked out on this so much. My husband was like, oh my gosh, hon, you are still working on this and it's 8 o'clock at night. I'm like, I keep finding all these pictures. I want to understand it. So luckily, he's used to me doing that kind of stuff. He gets used to it. So we're going to go to the menu. And we have to get some sort of axis, like time axis, x-axis, pick your point of view. And so we're going to go ahead and go to points and lines, make ourselves a little segment right here. And I'll concede, I might not do this perfectly the first time, but we have the ability to adjust it with technology, which is something that I think is great. So I'm going to start on the original cue ball, and I'm going to put this point out here like so, realizing I might be moving this somehow. So this is the x component of our momentum vector, or of our velocity vector, because again, we can talk just about velocities right here because our masses are equal. So we have our x component, and what we want to do is make these perpendicular y components. Well, again, geometry teacher me says, oh, I know how to do that. I'll go into menu. Finding perpendiculars are a type of construction, so I'll go into that perpendicular, and I'm going to click on the ball. I'm going to click on the segment, and there we go. There's one. I'm going to click on this ball. I'm going to click on this segment. There's another one. And I'm going to click on this ball right before it hits that side of the table. And I'm going to click on this as well. Now it says intersection point there, and I do want to do that. But I found that sometimes if I click it in that moment, it doesn't always register. Maybe that's something that's my fault. But I'm going to just go ahead and make sure I've got all my bases covered. So I'm going to find all these intersection points between the perpendicular lines and my original x-axis or time axis. My parallel to the stick axis, we'll call it that. So now what I'm interested in is these velocity vectors. I want to understand what is happening with the y components of all of them. So that seems like a magnitude question. I'll go ahead and go into menu, and let's measure the length. Find this magnitude. So the magnitude of this vector, that vertical vector, is 1.45. The length or magnitude of this vertical vector is 2.45, disregarding the centimeters. And the length of this vector is 4.75. And that's right there is why there's an undo button. Okay. I always remind my students that I do that to make them feel at ease because they'll make mistakes too. And then I'll hit escape. And when we look at this right now, if I mentally add that up, I have about 3.9. So there must be something with the way that ball was hit, because we know with the law of conservation of momentum that if my masses are equal, then my sum of my positive y vectors should match, or perpendicular vectors, should match the sum of my negative y vectors. They should be equal and opposite. So I'm just going to grab this. I'm going to do a little adaptation here. There we go. Yep, definitely in the wrong direction. Students do that too. Again, I like to remind them that I'm human as well. We bring this down. And now I'm at about 4.1, 4.2, maybe a little farther down. And eventually we get it to balance. So they can actually work on adapting this and understand conceptually this idea of the law of conservation of momentum. And why is it that we're able to work just with the velocity vectors? Well, it's because we have these masses that are the same. Since the green ball hasn't been moving the whole time, sorry, I'm going to make sure I can see this whole chat. Jackson says, since the green ball hasn't been moving the whole time, if we project its motion back to time 0, it might not be on the horizontal line. That's a great question. It actually lined up. Motion Shot does come with some glitches. It's a free app, so sometimes you have to be careful and take a picture before you ever start. But Jackson, we actually had set it up so that the purple and the green ball were right next to each other, right here on our segment that looks like it's an extension of the stick. But that's a great question to ask. What I'm going to do right now is I'm going to switch back. It's like those take and bake or those TV shows about cooking. I've actually got a nice picture over here where I played around with the numbers a little more. So I want to take just a moment to give you a moment to reflect, about 30 seconds to reflect on what was the STEM in this activity. So where was the science, the tech, the engineering, the math? And I want to get your thoughts on this. So 30 seconds of me quiet so that I can go ahead and get your thoughts. There's my 30 seconds. Get to check out what everybody says. Definitely, we're working on the idea of conservation of momentum in this problem. So the science is pretty right there. And then we've got vectors, which are these beautiful overlap between math and science. We love to each claim them as our own, right? And then we've got this technology using the geometry app, which, like I said, when I first started teaching physics, I didn't see how geometry was, the app was going to to apply to this. And then I found that I'm using it all the time because it's so helpful in making sense of these. And Jackson, same. Like I teach geometry constructions as a geometry teacher, and then I think sometimes people think that that's the part that can be omitted. Like, well, they don't really need to know how to make a perpendicular, but in real life, that seems to be something that's a real good life skill. Whether you're I don't know, building a fence and you want it to actually stand up straight, or you're analyzing some sort of physics situation. And we're using the positions, exactly right. We are using a picture with positions because we've got the velocities. So we have all these different ideas, but no one has said anything about the engineering part. So I want to push you. Based on the story of at the very beginning of this, students had to find a way that they were going to capture these moments of what was happening on the pool table. Can anybody think of any engineering that might have happened? Kathy, that's what it ended up being. The biggest thing about this engineering challenge was, where do you put the phone? How are you going to take this picture? How are you going to make sure that everyone sees it? Because that's a real life problem. If we only have one of these pool tables, how does everyone get access to the experiment so that they can form their own thoughts? And I think that's a great problem solving thing for students to think about, is this idea of who gets the access. How do you make sure everybody gets access? And so that was the engineering feat. And while it ended up being solved by having a tall kid stand on a chair, not a rolly chair, that would have been terrible. But it was something that required them to come up with a solution. Kathy, I'll tell you what, Motion Shot, it's been an app that I've really enjoyed using. I just went on to whatever app store that you have and looked up Motion Shot by Sony, and then you just press play on it like you would for slow mo on your phone, and then it creates these images. I'm a big fan of finding things that help me slow down what's happening so that kids can analyze individual pieces of it. So the last thing is, one more thing about Motion Shot that I did is we gave the kids a challenge of finding, they had to use a slinky, and we attached a weight to the bottom. We were trying to get them to understand what's happening with the slinky. Of course, if you stand there and you just move a slinky back and forth in one spot, it's a little bit challenging to fully understand what's happening with it. So we said, how would you get a better sense of what the slinky is doing over time? And so I want to give you just a moment to look at this picture. What do you think students reply to the question? What do you think a slinky is doing over time? What do you think the reply was to that? This is what they created. This is the product. What do you think their reply was? So I'm going to stop for 30 seconds and give you a chance to respond, and then we'll chat about this. And unfortunately, our time will end, but I know there's awesome sessions coming after this that I'm planning on going to. So. Okay, so can anyone think about what the students were able to do? So they were starting to say, well, there's got to be something with amplitude with this whole thing, because it's growing and then it's shrinking and it's growing and it's shrinking, and that feels like a wave to us. But the most interesting thing was that they weren't quite sure how to see it over time. And so you might see in the background there's some waviness here, a little waviness here. This is actually someone walking behind this board with their little slinky spring, essentially. So they built their own slinky spring. They used motion shot to capture it. The reason there's a board, there was a little engineering involved here, is that they realized if they just had the person's body right behind the slinky, then all you would see is the person's body and not the actual weight going up and down. And so students said, we've got to fix this somehow. And they put the board up. That was the fastest engineering. So we imported this into a graph. We did a curve fit, and you'll notice that it doesn't work right. And we said, well, why isn't it working? Math, I thought, always fit all the dots, and you could always come up with a regression. And they said, yeah, but that means that they were walking different. And this idea of understanding that this is not exactly consistent over this time period, that was a great thing for them to realize it. So we actually asked the kids, based on what you know about motion shot and about this graph right here, how could you go in and revise your experiment and then try it again? That iteration that Sean was talking about earlier that we don't always get time to do, this ended up becoming a big part of this project. And you'll notice in almost all of these, there's 3 people needed. It seems to be like the optimal group because there's 2 people to do something and 1 person to kind of wrap it up or record it. So as we draw to a close, I want to challenge you. This is a snapshot of what STEM curiosity looks like in our classroom, but I hope that by just seeing the regular objects being employed in this, that you also get a chance to think about what's around your house. What do you have easy access to? What do kids have easy access to so that they can continue to be curious about STEM this month? If you're like Ohio, you're going to be around your house a lot this month. So, what can kids look at and start to be curious about? What can they explore on their own? What does this look like for the rest of the school year, whether it's in person or online? I'd really, really love to hear your thoughts on it. And I know that the chat will not give us enough time to do all of that. So here I am. I'm on Twitter, Rachel H. Gorsuch. Or you can email me because I hope that this conversation continues after today as well. I know we're all going to need support during this time as we think creatively about the next best lessons that we're going to do with students. So I hope you take time to reach out, and I'd love to hear from you. There's a couple supports at the bottom as well. But I'm going to go ahead and turn it back over to Eric, and he'll wrap it up. But I just want to say thank you, and I can't wait to see what you do.